Sound waves, which are longitudinal waves, propagate with the vibrations of the particles of a medium in the direction of propagation of the waves. Sound waves in air consist of propagating compressions and rarefactions of small volume elements of air. In the region of compressions, there is an increase of pressure delta P, due to which the volume V of the elemental volume decreases by delta V. The volumetric strain of the elemental volume is denoted by the ratio between delta V and V. Bulk modulus B is expressed as the change in pressure by volumetric strain, which is equal to minus delta P by delta V by V. Let this be equation 1. The SI unit of pressure is Newton per meter square or Pascal. The dimensional units of pressure P are kilogram meter per second square into meter raised to the power minus 2. That is, the product of M, L, T raised to the power minus 2 and L raised to the power minus 2. Dimensional units of change in the pressure delta P is equal to the product of M, L raised to the power minus 1 and T raised to the power minus 2. Let this be equation 2. In the region of compressions, there is an increase of pressure delta P. There is a decrease in volume delta V and an increase in density. The dimensional units of density are kilogram per meter cube. That is, the product of M and L raised to the power of minus 3. Let this be equation 3. Let us now find the dimensions of bulk modulus B by density ρ to arrive at the dimensions of velocity V. From equations 2 and 3, we get B by ρ is equal to M, L raised to the power minus 1 and T raised to the power minus 2 by ML raised to the power minus 3. B by ρ is equal to the product of L square and T raised to the power minus 2. This can be written as L into T raised to the power minus 1 whole square, which are the dimensional units of V. Therefore, V can be written as the product of C and root B by ρ, where C is a dimensionless constant, which is equal to 1. This can be written as V is equal to the root of B by ρ. Let this be equation 4. Equation 4 implies that the speed of a longitudinal wave in a fluid depends only on the bulk modulus and the density of the fluid. Instead of a fluid, if you consider a solid bar as the medium, Young's modulus Y is used in place of bulk modulus B, as sideways compression or expansion of the bar is negligible. Only longitudinal strain is considered and the equation is modified to V is equal to root Y by ρ. Let this be equation 5. The table shows the speed of sound in various media. From this table, we find that the speed of sound in liquids and solids is higher than in air. The reason is that the densities of liquids and solids are higher than the density of air. Liquids and solids are less compressible than air and therefore have a greater bulk. Liquids and solids are less compressible than air and therefore have a greater bulk modulus, resulting in a higher value of B by rho. Newton tried to find the speed of sound in an ideal gas. Assuming that the gas undergoes isothermal changes while a sound wave propagates through it. Isothermal refers to equal thermal conditions, meaning a constant temperature that is maintained while energy propagates through the gaseous medium. For an ideal gas, under isothermal conditions, the relationship between pressure P and volume V is expressed as PV is equal to the product of NKBT, where N is the number of gas molecules in volume V. Kb is the Boltzmann constant, and T is the absolute temperature of the gas. The quantities on the right-hand side of the equation are constant. Hence, PV is equal to constant. The above expression leads to delta PV is equal to 0. This implies that V delta P plus P delta V is equal to 0. This can be written as V delta P is equal to minus P delta V. V delta P by delta V is equal to minus P. Once again, this equation can be written as delta P by delta V by V is equal to minus P. Therefore, minus delta P by delta V by V is equal to P. The left-hand side of the above expression is nothing but the bulk modulus B of the gas. Substituting this in the equation for the velocity of sound in air, V is equal to root P by rho. Let this be equation 6. Thus, the speed of a sound wave in an ideal gas is denoted by equation 6. As this equation was given by Newton, it is called Newton's formula. Let us now calculate the velocity of sound in air using Newton's formula. The density of air is the product of the mass of 1 mole of air and its volume. Let this be equation 1. Mass of 1 mole is 29 into 10 raised to the power minus 3 kilograms. And its volume is 22.4 into 10 raised to the power minus 3 meter cube at standard temperature and pressure. By substituting the values in equation 1, we get rho is equal to 1.29 kilograms per meter cube. We know that atmospheric pressure P is equal to 1.01 into 10 raised to the power 5 Newton per meter square. Substituting the values of 2 and 3 in Newton's formula, we get the velocity of sound in air at standard conditions of temperature and pressure, according to Newton's formula, is V is approximately equal to 280 meters per second. But the experimental value of the velocity of sound in air at standard temperature and pressure conditions is nearly 331 meters per second. This means the value derived from Newton's formula is about 15.4% less than the experimental value. This variation in magnitude in the experimental value and the calculated value cannot be attributed to experimental errors. Hence, there arose a need to revisit Newton's assumptions on deriving the expression for velocity of sound in gases. It was Pierre-Simon Marquis de Laplace, a French mathematician and astronomer, who pointed out that the speed of sound in air depends on the heat capacity ratio. This is because the changes that take place in air or any gaseous medium while sound propagates through it is adiabatic and not isothermal as assumed by Newton. Adiabatic change is a change that takes place without the exchange of heat. Sound propagates in the form of compressions and rarefactions. Compression leads to heating and expansion leads to cooling as the sound propagates through the gas. Laplace pointed out that pressure variations in the propagation of sound waves are so fast that there is little time for the heat flow to maintain a constant temperature. Hence, these variations in pressure are adiabatic and not isothermal. For an adiabatic process, the ideal gas satisfies the relation P into V raised to the power of gamma, which is a constant, where P and V are the pressure and volume of the gas. Gamma is the ratio of specific heat capacities, ratio of specific heat at constant pressure Cp to that of specific heat at constant volume Cv. Cp by Cv of the gas. The above equation leads to delta P into V raised to the power of gamma equals to 0. This implies that P into gamma into V raised to the power gamma minus 1 into delta V plus V raised to the power gamma into delta P is equal to 0. This equation can be written as the product of P, gamma, V raised to the power gamma minus 1 and delta V equal to minus V raised to the power gamma into delta P. Therefore, P into gamma is equal to minus V raised to the power gamma into delta P by delta V into V raised to the power gamma minus 1. On further simplifying, we get P into gamma is equal to minus delta P by delta V by V. Thus, the bulk modulus of the gas is P gamma and not just P as Newton arrived at while deriving the expression. Thus, the velocity of sound in an ideal gas after Laplace's correction is expressed as V is equal to the root of gamma P by rho. Let this be equation 1. The value of gamma for air is 1.4. Substituting the values of gamma, P and rho for air in equation 1, we get the value of sound V in air as approximately equal to 331 meters per second. The speed of sound in air at standard temperature and pressure conditions thus obtained implementing Laplace's correction is in agreement with the experimental value. Let us consider two pulses traveling simultaneously along the same stretched string in opposite directions. The net displacement of any element of the string as the two pulses cross each other is the algebraic sum of the displacements due to each pulse. After crossing each other, the pulses move forward unchanged. The addition of the waveforms or pulses to find the net or resultant waveform is known as the principle of superposition. y1 of xt represents the displacement of any element of the string at time t due to the first wave. y2 of xt represents the displacement of any element of the string at time t due to the second wave. Let us now consider two waves traveling simultaneously along the same stretched string in opposite directions. When the two waves overlap, we have y of xt representing the displacement of the string in the overlap region at time t. Mathematically, we can write this as y of xt is equal to y1 of xt plus y2 of xt. This expression implies that overlapping waves algebraically add up to produce the resultant wave. Let us consider an example to observe the effect of the superposition of waves. When the waves are propagating in the same direction along a stretched string, both the waves have the same angular frequency, omega, and angular wave number, k, as they are propagating on the same string. They have the same amplitude, a. Their phases at a given x and t differ by a constant angle phi. By changing the angle phi, we can observe different net waveforms. That is, when phi is equal to 0, we find that the amplitude of the net waveform is doubled. When phi is equal to pi, the two waves are completely out of phase, and therefore the amplitude of the net waveform reduces to 0, and we get a straight line. When the value of phi is between 0 and pi, the amplitude of the net waveform keeps changing from 2a to 0, where a is the amplitude of the original waveform. The net waveform shifts by phi divided by 2. These observations can now be expressed mathematically. The first wave is represented by y1 of xt is equal to a into sine kx minus omega t. Let this be equation 1. The second wave is represented by y2 of xt is equal to a into sine kx minus omega t plus phi. Let this be equation 2. The second wave is shifted by a phase angle phi from the first wave. From equations 1 and 2, we can say that both waves have the same angular frequency omega, the same angular wave number k, and the same wavelength lambda. the velocity of the waves propagating on a single stretched string is same. This is because the velocity of the wave on a stretched string depends only on the tension T in the string and its linear mass density mu. The velocity of the wave is expressed as the root of the ratio between T and mu. And in one stretched string, T and mu are constant. Now we can apply the principle of superposition of waves to arrive at the expression for the resultant waveform. By adding equations 1 and 2, we get y of xt is equal to a into sine kx minus omega t plus a into sine kx minus omega t plus phi. Let this be equation 3. Let us consider the trigonometric relation, which is similar to equation 3. Let this be relation 4. Applying relation 4 to equation 3, we get y of xt is equal to 2a cos phi by 2 into sine kx minus omega t plus phi by 2. Let this be equation 5. From equation 5, we find that the resultant wave is also a sinusoidal wave, which is propagating in the positive direction. There are two differences between the resultant wave and the constituent waves 1 and 2. The resultant wave has a phase angle equal to half of phi with respect to the first wave. The amplitude of the resultant wave is equal to 2a cos phi by 2. We can now apply these mathematical expressions to compare with our actual observations. When phi is equal to 0, the amplitude of the resultant wave is equal to 2a. And the two waves are in phase. And equation 5 becomes y of xt is equal to 2 into a sine kx minus omega t. Let this be equation 6. Comparing equations 1, 2 and 6, we find that the amplitude of the resultant wave is equal to twice the amplitude of the constituent waves 1 and 2. When phi is equal to pi, the two constituent waves are completely out of phase, and equation 5 becomes y of xt is equal to 0. Let this be equation 7. Equation 7 indicates that the resultant wave has 0 amplitude. That is, the wave is a straight line. When a pulse of a traveling wave strikes a rigid boundary, it gets reflected. An echo is one of the simplest examples of this phenomenon. If the boundary is not completely rigid, or if it is an interface between two different elastic media, a part of the wave is reflected, and a part is transmitted into the second medium. Reflection of waves follows the laws of reflection, which are similar to the laws of reflection of light. To understand the phenomenon of reflection of waves, let us perform two simple activities. In the first activity, the left end of a string is fixed to a rigid wall. In the second activity, the left end of the string is tied to a ring which can slide up and down without any friction on a rod. A single pulse is generated at the free end of the strings. In the case of the first activity, the pulse, on reaching the left end of the string, encounters the rigid wall. The pulse applies an upward pull on the wall, and the wall applies an equal but opposite downward pull on the string, obeying Newton's third law of motion. The downward pull by the wall on the string generates a pulse which travels in a direction opposite to that of the incident pulse. As there is no displacement of the particle at the junction of the string and the wall, the incident and reflected pulses have opposite signs and cancel each other at that point. Due to this phenomenon, the reflected pulse has a phase reversal or a phase difference of pi or 180 degrees. In the second activity, when the pulse reaches the end of the string, it pulls the ring up. As the ring moves up, it pulls the string, producing a reflected pulse with the same sign and amplitude as the incident pulse. In this process, the incident and reflected pulses reinforce each other, creating maximum displacement at the end of the string. The reflection is without any additional phase shift. Let us now express these observations mathematically. The incident wave is represented by yi of x t is equal to a sine kx minus omega t, where a is the amplitude and k is the wave number of the wave. The reflected wave from a rigid boundary is represented by yr of x t is equal to a sine kx plus omega t plus pi, which is equal to minus a sine kx plus omega t. For the reflection at an open boundary, the reflected wave is represented by yr of x t is equal to a sine kx plus omega t. When a wave is incident obliquely on the boundary between two different media, we know that a part of it is reflected and a part is transmitted to the second medium. This transmitted wave is called the refracted wave. Refraction of waves follows Snell's laws of refraction, as in the case of a beam of light.